Hi everyone, I'm Professor Burgasser, and in this video we're going to be looking at two-dimensional collisions, looking at the motion of particles as a result of collision that takes place in two different dimensions. And remember, we're going to be approaching this from our momentum and energy perspective. The momentum perspective is particularly important because when we look at a system of two or multiple particles, what happens in terms of the internal forces between those particles can be as complicated as they can be, but we don't have to worry about those internal forces in terms of calculating the momentum of the entire system before and after the collision. So we're going to approach this in the same way that we've done one-dimensional collisions, but making sure we take into account both directions of motion for the momentum vector. So we'll set up our problem looking at what are the numbers that are known, figuring out what are the target numbers we're looking for, and then making some predictions about the motion if we're able to do that. Then we're going to break up our problem into different acts and identify what are the systems that define each of those acts. Those acts, of course, could include a collision event, but also other motions throughout the system. For each of those acts, we're going to write an initial and final momentum, and we're also going to write the initial and final energies for the entire system. And then we're going to look, see if there's any external or dissipative forces in the problem, because those forces will play a role in setting the changes of the momentum and the total energy through our momentum impulse and work energy theorem. And that's step number 5 there. Keeping in mind that for the two-dimensional problems, we're going to have to write down the momentum in two different directions and look at both of those components separately. And then finally, once we solve for our unknowns, we're going to check that our answer makes sense, both in terms of the units and also the predictions that we made ahead of time. And if we have a relationship, we can look and see if that relationship makes sense for extreme values of the parameters that we're interested in. For our first example, we're going to take a look at a famous experiment, the 1911 Geiger-Marsden experiment, in which alpha particles, which are essentially helium nuclei, were shot at a target of gold atoms. And the idea was that these alpha particles would be small enough that they would pass right through the gold bar and measured as a deflection on the other side. However, what was actually observed was that these alpha particles were deflected over very large angles. And that observation, this large deflection, really proved the existence that atoms are made out of very dense, compact nuclei with a cloud of electrons surrounding it. So this was a famous experiment for understanding the structure of the atom. Now we can approach this from a two-dimensional collision experiment and ask the question, if we have a helium nucleus that makes a 90-degree deflection with an interaction with one of the gold nuclei, how does that gold nucleus respond as a result of that interaction? So we can look at this from different perspectives, but let's follow our regular process for how we solve these kind of problems. The first thing is to make sure we can take a note of what are the things that we know. And the things that we know are the mass of the helium and gold nuclei, because they're given by the atomic numbers, which are indicated in superscript up there. So the helium nucleus is made up of 2 protons and 2 neutrons. That's 4 nuclei. And the gold nucleus has a total of 107 nuclei. So that's a good measure of the relative masses of those two particular atoms. We're also told the deflection angle of 90 degrees for the angle in which the alpha particle is deflected away. And then we're asked to calculate the what angle and what speed the gold nucleus is deflected. So we're really looking for the angle in which that second particle, the gold nucleus, is deflected and its speed as the alpha particle is deflected off at 90 degrees. All right, so now we can start to break down this problem into its series of events. And really we're looking at just one event, and that's the collision between the alpha particle and the gold nucleus. So the only event we're worried about is the collision between 4He and 197Au, and that is a 2D collision. And we're also told that there's no energy dissipated in this interaction, or to assume that. And so that means it's also an elastic collision. All right? So we can use both of those pieces of information to start to calculate what some of the variables are for this particular collision. And the system that we're looking at, of course, then is the 2 nuclei that come into contact, the helium nucleus and the 197 gold nucleus. That's the system we're going to be looking at in terms of this collision. Now in terms of predictions, well, we can think about the fact that this gold nucleus is a much, much heavier nucleus than the helium nucleus. So even though the helium nucleus is being deflected by a very large angle, we can make an assumption or a prediction that the speed of the gold nucleus after the collision is probably going to be very small compared to the initial speed of the helium nucleus. So we'll see if that prediction actually bears out when we go through our calculations. All right, so for this one event, this collision, this 2D elastic collision, we're going to write down the initial and final momenta along both the coordinate axes and the initial and final energies. So let's draw schematically what's happening here. We've got a helium nucleus that's coming upward with some speed, and we're actually given that speed. That's one of the knowns that we're given, 0.06 times the speed of light. So we'll just write that down. We can convert c into a real number a little bit later. And we're assuming that the gold nucleus inside the target is at rest, at least from the perspective in which we're looking at the experiment. So this is our initial condition here. Our final state is the helium nucleus traveling out with some unknown speed, which we'll have to calculate, and the gold nucleus also being deflected, and I'm going to make a guess that's deflected in some direction that way. And of course, the number that we're interested in calculating is both that speed, the velocity after the collision of the gold nucleus, and the angle relative to the horizontal in which that gold nucleus is deflected. So this is our final case. All right, so now let's start to write down our initial and final momentum along the different axes. So I'm going to make sure I set a coordinate axis here, and I'm going to choose x to go in the horizontal direction and y in the vertical direction on the board. And so we can write down our x momentum. That's going to be 0 in our initial case because the alpha particle is moving straight vertically, at least in this diagram. In the final case, we're going to have all of the momentum of the helium nucleus, so the mass of the helium nucleus times its speed, and we're also going to have a minus the mass of the gold nucleus times its speed times the trigonometric function of the angle. And if we look at this carefully, we're looking at this axis, so that must be the adjacent side for the angle. That's the cosine of our angle, cosine theta. Okay? Now let's write down our y coordinates. In this case, all of the momentum is in the initial speed of the helium nucleus, so we're just going to write down that symbolically. And then on the post-collision here, the only y momentum we have is the y momentum of the gold nucleus itself. So we can write that down, MAU VAU prime. And just to keep in mind, I'm using prime to denote the post-collision velocities, so we can keep track of which ones we're talking about. And then we have to write down the angle component, and this is going to be a sine theta because it's the opposite of our cosine angle. All right, so just to take stock, we've got 1, 2, 3 unknowns and only 2 equations. So we need to write down a third equation. And of course, that third equation is going to be the total energy of the system. And that's the kinetic plus the potential energy. In this case, we're not really dealing with anything in terms of potential energy because we have no external potential forces. We're not doing this experiment in the gravitational field. So even though it's shown vertically here, we can assume this is on a flat table. And so we're really just looking at the kinetic energies of these particles. And that's pretty straightforward to write down. It's 1/2 mhe VHE squared for the initial, and 1/2 mhe VHE prime squared plus 1/2 MAU VAU prime squared for the final kinetic energy. So now we have 3 equations, 3 unknowns, and we can solve for all of our unknowns using these equations. We just have to figure out the best strategy to do that. Well, let's start with the momentum equations because they seem to be the easiest to work with. I'm going to take this first equation, Py, and I'm going to isolate our initial velocity for our helium nucleus, or our alpha particle, because that's a known quantity. And I'll set that equal to the other side by just dividing by the mass of the helium nucleus. So that's now VAU prime times the mass of the gold particle divided by the mass of the alpha particle times sine theta. So now we've got VHE as a number in terms of VAU prime. And I can also write down the speed of the helium nucleus after the collision in terms of the gold nucleus speed, by using this equation, 0 is equal to this quantity. I should make sure I make it clear that all of these are equal to each other because there are no external forces and there are no dissipative forces. So these are all equal to each other. So I can use this equation here and just move over this term to this side and then divide by MHE, and I'm going to get the speed of the helium nucleus after the collision is again equal to the speed of the gold nucleus after the collision times this ratio of the nuclei masses times cosine theta. All right. All right, so now we've got these two terms in terms of the same gold nucleus speed. Our next step is to plug it into our energy equation and solve for the unknowns there. So now starting from our energy relation, we can plug in the expressions we got for our velocities of the helium nucleus before and after the collision. First, we can notice that we can cancel out all of our 1/2s here because they are the same across. And if we divide by MHE, we can cancel those out and write this in terms of the fraction between those two numbers. And then we can go ahead and plug in our expression for the speed of the helium nucleus before and after the collision. So once we start to put all those numbers in, we get this VHE squared here is the gold nucleus after collision squared times the combination of the mass ratio squared times sine squared theta. And that's equal to the, again, gold nucleus after the collision squared ratio of the masses squared times cosine squared theta. And we've got one more term here, which is just our original speed of the gold nucleus times the ratio of the masses, but just left alone. All right, so now I can do a little manipulation. We can see right away that all of these speeds cancel out, so that gets rid of a pretty difficult factor there. If I subtract the cosine squared term over and divide by this ratio of masses squared, we're going to get sine squared theta minus cosine squared theta is equal to the inverse of this number, MHE over MAU. And if you know your trigonometric identities, you'll recognize this as minus cosine of twice the angle. This is equals minus cosine times 2 theta. So that gives us theta is just 1/2 times the inverse cosine, and I should say this is of minus MHE over MAU. And we have expressions for those masses. It's just 4 over 197. And so if you throw all these numbers in, what you'll find is you get a number that's equal to 45.6 degrees. And I'm giving it in slightly higher accuracy than I actually know my numbers, just to kind of give an idea of how close it is to 45 degrees. If the masses of these particles, if the gold nucleus, for example, is much, much larger, this will get closer and closer to 45 degrees because this number here will get smaller and smaller, and we get closer to cosine of 90 degrees because cosine 90 degrees is close to 0. So we're very close to that. We have exactly almost a 45-degree angle, which this gold nucleus is ricocheting. And if you think about it, that kind of makes sense. If this alpha particle is doing exactly 90 degrees, it kind of pushes off at a 45 degrees angle from the gold nucleus. So that's about what we would have expected, even though we didn't explicitly make that prediction. So let's put a box around that. Now we can go back and calculate the speed just by using one of our original expressions here. We know in this case, for example, the speed of the helium nucleus beforehand. So let's rewrite that equation to give us the speed of the gold nucleus afterwards. That's just VHE times the ratio MHE over MAU, and then 1 over sine theta. But of course, sine theta is this angle, and this number is 0.06 C, and this ratio is just 4 over 197. So when we put all of these numbers in, we get a value of 0.014 times C. And again, C is the speed of light. So if we put in the value for that, which is 3 times 10 to the 8 meters per second, we'll get a value of 4 times 10 to the 6 meters per second, approximately. All right, so that is indeed much, much smaller than 0.06 c. It's about a factor of, well, let's call it maybe 5 or so smaller. But it's still a really huge number, right? That's 4 million meters per second. And so even though this gold nucleus apparently doesn't move out of the nucleus itself, it is knocked with a very large velocity. Now what keeps that gold nucleus in place is the very strong bonds that occur inside the gold metal structure. And so that starts to give an idea of how strong those bonds are, given the fact that these alpha particles are not able to actually knock them out, even though they give them very large velocity kicks. In any case, we are able to match the predictions. We've got the units that we expected, and we get some insight into how energetic this interaction is. It's actually quite powerful. It knocks the nuclei quite strongly to get that 90-degree deflection, and yet those gold nuclei don't actually go anywhere. So we get some information about the structure of the atom, as well as some idea of the sort of quantitative nature of the interaction itself. So let's look at a second example that's a little more down to earth, and that's looking at a common example where we look at collisions, and that's at the pool table. If you are a pool shark, you might have all sorts of neat little tricks to sink multiple balls into the pool holes. But let's see if we can just try to figure out the physics of one very simple one, where we knock one ball into another and try to sink both of those balls into their opposite corner holes there. So to add a little spice to this problem, I'm going to add in a coefficient of friction between the rolling balls and the felt on the pool table. There is usually some kind of friction, slowing friction down for these cases. That's why you can only shoot a pool ball so far. And so we'll take a coefficient of friction, an effective coefficient of friction of 0.010. It's a very low friction coefficient, and that's what allows these balls to roll quite far. But of course, eventually they do come to a stop. So we do have a dissipative force in this problem, and we'll see how that affects the solution. Now, as always, it's important to look at what are our knowns and unknowns. Numerically, we're really only given the coefficient of friction, which is 0.010. But we're also given some of the dimensions of the problem over in the diagram, so that the distance between the white ball and the black ball initially is about 0.3 meters. The distance between the black ball and the far wall is about 0.5 meters. And then the angles at which these two objects have to go off are given by 30 and 45 degrees based on our diagram. So we've got quite a lot of the geometry already set for us. We just have to figure out what speed we have to knock this ball in to get both those balls into the holes. All right, so we have a couple of events that are actually happening. If we think about sort of the process by which this whole mechanism takes place, the steps that are happening here are the following. We've got first the white ball approaching the black ball, and we've talked about that there's friction acting in this problem, and so this is really an example of one-dimensional motion with constant acceleration, that constant acceleration being provided by the kinetic friction. So that's the type of problem we're talking about, 1D accelerated motion. And clearly something we've seen before. The second event is the collision between white and black balls. And we're not given really any information about whether this collision is elastic or inelastic. Clearly when you play pool you can hear the balls knocking each other, so some energy must be lost. So we're not actually giving that information, so we may have to see how we can back that out from the geometry of the problem itself. And then of course the final act is both balls rolling into their respective holes. And again, this is an example of 1D accelerated motion. And it comes with a constraint that those balls have to have enough energy, kinetic energy, and enough sort of dissipative work done so they still have some kinetic energy at the end so they actually make it into the hole. So that's going to give us a constraint on what our final velocity is for these balls, and that will constrain the initial velocity when we strike the white ball. Okay, so let's go through this event by event, and let's start and go in order. We'll look at this first 1D constant acceleration problem. Just for completeness, let's go ahead and go through the whole process of looking at the forces that are acting on the white ball as it's rolling and approaching the black one. So we draw a little force diagram here. In this case, we're now looking sideways along the table. So up vertically against gravity is up on this diagram. And so we can draw the forces that are acting on here as the weight force that's acting on the ball, because it is in gravity here on near Earth. We've got a normal force in the contact between the table and the ball surface. And we've already mentioned that there's a friction force acting. And based on the drawing, since the ball is rolling in off that direction, we can assume that that friction force is pointing in the opposite direction of the motion. So we can then choose our coordinate system for this simple 2D diagram, where I'm going to let the x-axis point in the direction of rolling motion. And now we can write down the forces that are acting on the ball and the equations of motions in these two different directions. So if I look at the y component, so that's vertical component, mass times acceleration in that direction is just equal to sum of the forces, which is the normal force minus the weight. And assuming that we're not jumping this ball off the table or it's not falling through, those forces have to cancel. And so we're given immediately an expression for our normal force, which is identical to the expressions that we've seen before in these kind of problems. Now we can solve for the motion in the x direction in which it's moving. The mass times acceleration is now just equal to the minus the friction force because it's acting in the opposite direction. This is minus mu times the normal force itself, so that's m times g. And so we're given an expression for the acceleration, which is minus mu g, which is, again, an expression we've seen before in these kind of friction force problems. So we've got a constant acceleration 1D problem. We can go back to our first cycle of physics and remember that we have our kinematic relations for 1D constant acceleration motion. So we can either write down the position as a function of time, or we can write down the speed as a function of displacement. And since we know the displacement is 0.3 meters and we're interested in speed, that seems to be the one that we want to write down the most. So let's go ahead and write down that expression. If you recall, that's the final speed squared is equal to the initial speed squared plus 2 times the acceleration times the displacement. And in this case, that's equal to the initial speed squared minus 2 mu g times 0.30 meters was our initial displacement between the white ball and the black ball. And in this case, the final speed is the speed at which the white ball hits the black ball, and that's going to be an important initial condition for the next event. The initial speed here is actually the quantity we're looking for. So we better underline that because that's an important number. But at this point, we can't uniquely solve for those numbers because we've really got two unknowns in just this one equation. So we can only write down the relationship between them. And I'm going to go ahead and rewrite this because eventually what I want is that initial speed. So I'm going to write this as the initial speed squared is equal to the speed of the white ball, which I'm going to write in this way because I'm going to get back to that for our collision. That's the speed of the white ball before the collision. And then plus 2 times 0.010 times 9.81 times 0.3 meters. When you write all those numbers out, you get 0.059 meters squared per second squared. Now let's double check our units. We've got meters squared per second squared. That's the same as velocity squared, so that's true. And that comes from writing down meters per second squared here times meters, so we get the right units. All right, so that's our first constraint of our unknowns. Now we're going to go to the next step to see if we can go down further and figure out what's the next number we can solve for. So with our first constraint on our unknowns, let's now turn to the next event, which is the collision between the white ball and the black ball. Now I've drawn the initial and final schematics of this collision. We've got the white ball coming in with some speed VW to a stationary black ball. That's our initial state. And then afterwards, these balls are traveling off at their specified angles, and we're hoping that they have enough velocity in order to make it to their destinations. So let's just figure out what happens between the velocities in these collisions by looking at this from a momentum-impulse relationship. Now, it's a 2D problem, so I'm going to have to write down the momentum in both directions. So let's first write down our momentum in the x direction In that case, let's make sure we also write down our coordinate system. We'll use the same one we had before, x hat and y hat, with the x hat pointing in the direction of motion. So in this case, the initial momentum then is going to be the mass of the white ball, which is the same for both, times its speed. And the final momentum is going to be the mass of the black ball times its speed times the component along the x direction, which is cosine of 30 degrees. And we're adding in the mass of the white ball, its speed after the collision, times cosine of 45 degrees. Both of these are along the adjacent side of these angles. Okay, so that's the x momentum. Let's look at the y momentum. In this case, we've got 0 as our initial y momentum, and we've got these going off in different directions, so they're going to subtract from each other. We've got mvb prime sine 30 degrees, and that is a minus because it's going in the opposite direction of our y-axis, plus mvw prime times sine of 45 degrees. Now, that's the initial and final momentum, and one thing to notice is that in these equations, I really only have two unknowns, which are the unknown speeds of the black and white ball after the collision. I've already basically constrained away anything I need to know in terms of the energy because of the angles. Now, these two expressions for the momentum are not yet related to each other. They're related by whether or not there is an external force acting. And we've already talked about that there is external force acting. There's a friction force acting from the table onto the system of the two balls that we're using. Now, in fact, when we think about it, the impulse, the changed momentum, is equal to that external force times the time over which this collision is taking place. So if we make the assumption that this collision is almost instantaneous, which means that that time scale is extremely short, then even if there is an external force, the time at which it overacts is not enough to significantly change the momentum of the two-ball system. So with that assumption that the time of the collision is very short, we can equate these two expressions together. And two equations, two unknowns, we can go ahead and solve for the unknowns without writing down our energy relationship. So let's go ahead and do that. Starting with the y equation, I'm going to isolate my VB prime here by noting that I can cancel out the masses. And in fact, I can do that for our top equation too. Moving that to this side, and that's just going to equal to the white ball velocity after the collision times this ratio, sine 45 degrees divided by sine 30 degrees. And when you put that into your calculator, that's 1.41 times the speed of the white ball after the collision. So the black ball is going to be moving faster than the white ball after the collision. We can then write down the speed of the white ball before the collision in terms of these numbers. And I can substitute in my expression for VB prime. So this is going to be 1.41 VW prime times cosine 30 degrees plus VW prime times cosine of 45 degrees. And again, if you put this in your calculator, write down all the numbers, you get 1.93 times VW prime. So I've been able to relate the speed of the black ball and the white ball together, and the speed of the white ball before and after the collision, but yet I still don't know what that speed of that white ball is, but I at least got it in terms of the other unknowns. So we can now take another step and see if we can use that last event to make a constraint on these different velocities for the balls after the collision. All right, now that we've solved for our velocities before and after the collision, we can look at our last event in our sort of process here, and that's the motion of the balls as they go into the holes. And this is, again, a 1D constant acceleration, where the acceleration is provided by friction. And in fact, that friction force is going to be the same for both of the pool balls because they both have the same mass. In fact, it doesn't even matter on mass, it just matters on what the coefficient of friction is between the surface of the ball and the table. So as before, we can just write down what the solution is going to look like for that. The final speed of the balls is going to equal to the initial speed of the balls minus 2 times mu times g times whichever displacement we're looking at. And now we can get to an actual constraint based on our problem The question was, what is the minimum speed that the balls must have, at least the white ball must have, for both of those balls to roll into the hole? And that means that that final speed in which the ball makes it to the end of its path has to be at least 0. It has to just make it as the minimum speed. So that sets a constraint as the final speed after this 1D acceleration. Now, here's a question. Which one are we talking about? Right? Which ball, white or black? Well, since it's the same acceleration from both, we can see which one is moving the furthest, because that's the one that's going to have the most work done on it, the most loss of energy through this dissipative force. So that's just a geometrical question. So we can look at delta x, for example, the black ball. That's just equal to this length, 0.5 meters, divided by cosine of 30 degrees, because we're really going along the hypotenuse of this triangle. So we know that the cosine of that angle is 0.5 meters. So I can divide by cosine of 30 degrees, and that gives us 0.58 meters. For the white ball, the motion, the side motion is the same, 0.5 meters, but now we're divided by a cosine of 45 degrees. And when you go through that calculation, you find that the white ball has to travel 0.71 meters. So it's really the white ball that we're most concerned with, because that's the one that has to travel the furthest. If the white ball can make it, so can the black ball. All right, so now this is just a matter of plugging in the numbers, because what we're really looking at is a case where the initial speed squared has to be greater than this expression moved over, greater than 2 times mu times g times delta x, and that's 2 times 0.010 times 9.81 meters per second squared times the displacement of the white ball, which is 0.71 meters. And when you put all those numbers in, you get that the initial speed squared has to be at least 0.14 meters squared per second squared, or the initial speed, and this is the initial speed after the collision of the white ball, so that's really W prime, VW prime, has to be greater than 0.37 meters per second. Now, it's just a matter of unwinding all of our calculations. We've got an expression for VW prime here. That's 0.37 meters per second. We can plug that into our expression for VW. So we're just multiplying that by 1.93. Then we can add 0.059 meters squared per second squared to VW squared. And just to cut all of this short, in the end, what we have to find is that the initial speed of the white ball has got to be greater than 0.83 meters per second. Okay, so 3 different steps, 3 different calculations, and in the end, we end up with that first initial speed by just keeping track of the numbers as we go along. Now, we should take some moment to think about whether this is a big number or not. 0.83 meters per second is not really a number we think about a lot. But keep in mind that the typical pool table is something like 8 feet across. That's something like 3 meters or so. And if you shoot a ball at 0.83 meters per second, it's going to take 3 or 4 seconds to get across. So that's actually not very fast of a pool ball hit. So this should be a pretty easy trick shot. It's something that you could probably do pretty easily, just as long as you've got your aim right. We haven't talked about aim at all in this problem. But at least in terms of speed, this should be a pretty easy one to make. So we've just seen a couple examples on how we apply both the momentum impulse and the work energy theorem to look at the results of 2-dimensional collisions. And the things I want to make sure you keep in mind is that you're looking at the components of momentum in both of those directions, but particularly those directions in which there are no external forces acting. In some cases we can just focus on those individual axes and solve the problem from those alone. In many cases we may have to look at energy, some cases we may not. It depends on what variables we're given. But in all these cases it's important to look at both the initial and final stages and also breaking up the rest of the problem into individual acts, because we may use other techniques such as kinematic equations, our force equations, our energy relations in order to solve those as well. So good luck with your 2-dimensional collision problems, and we're going to see more as we get into our homework.